In this lecture, I will discuss the method of selective inference. Basically, we already looked at that when we discussed the covariance test, because it's one particular form of selective inference. Selective inference in general is inference where we condition on the selection of a specific model. So for instance, we could want to construct a confidence interval in such a way that the conditional probability that given that we have selected a particular model, that coverage probability is at least 1 minus alpha. Now this is, of course, is a very natural way to think about coverage probabilities and guarantees for honest inference, given that what we do is a two-step procedure, so it makes natural sense to start conditioning. And in a way, this is also very much related to sample splitting that I discussed earlier, even though it's hard to see this up front. Where sample splitting also, by separating the sample you use to select your model and to then do inference on the parameters, you're also essentially conditioning on this decision. So we're conditioning, and then because we use separate samples, there actually, of course, the calculation becomes much simpler, because conditioning then will not actually have any effect because the two are independent. Now, here we want to make it a more general idea, and rather than doing sample splitting where you lose half of your sample, you really want to explicitly derive these kind of conditional statements. So for the covariance test was, well, there we conditioned on the currently selected predictors. And then what we wanted to do was conditional on that, thus adding one more yields a significant improvement. Now we're going back to the original framework, and that is doing inference on the parameters. And so we are going to use the same notation as for the POSI. So you see also that the notation here is the same. And in fact, we also take the same submodel view. So that is one consequence of doing selective inference. And that is implicitly what we also did actually in sample splitting, is if we want to give it a uniform and honest interpretation, we have to do it on the submodel view. Now I think it's very natural actually here in the conditioning framework, because, well, given that you condition on that particular model, it also makes sense to give meaning to the parameters in that particular model. Now there are many papers about selective inference. I'm going to focus on one in particular, which applies this idea to the lasso to be able to do confidence intervals, conditional on which variables end up in your active set. Of course, these conditional probabilities are complicated because we do not only need to take care of the first part, but also of the second part. And we need to say something about the probabilistic structure of that. And that, of course, is very general, very complicated in general. Now, it turns out that there are cases where you can make this, it becomes manageable, and the lasso is one of these. And so in particular, what this paper does, it uses again the first order conditions of the lasso, which turn out to be very important across methods, and is going to play with those. The first order conditions, remember, have this form. We've already used them for the disparsified lasso. Now I put a hat here on the S to indicate that this is the value for the subdifferential that we get in this particular sample. So therefore it's a hat. You could see it as the estimated sign because it corresponds to the estimated parameters. Now we know that, of course, for any parameter that has been selected, we know that the sign is either 1 or -1. So you will not end up with a subdifferential there. That would only be if you would not select that parameter, if its coefficient is 0. So we know that if we let S hat denote all the selected variables, all the ones with coefficients not equal to 0, then also note that what we get is that the signs in absolute value always are equal to 1. Right? Either 1 or -1, depending on the sign of that. And also note that, in fact, this set of taking out all the variables which have a sign equal to 1 in absolute value is almost equal to the set of selected variables. In fact, it is generally equal except at the nots, because at the nots is where we just add one variable and then we have not set its sign yet, because its coefficient is still 0 point, but the variable has been added. But that is the only difference between these two sets. And it turns out that we can use that to do inference. So what they do, and that is where they make their breakthrough, is, well, now let's not just consider the event to condition on that s hat is equal to s, but let's also condition on the signs having their particular values. So s here is a vector of 1s and minus 1s, which then of course corresponds to the signs in s hat. So the event that we're going to condition on is not just selecting their variables, but also choosing their signs. And then they do some algebraic manipulations of these first order conditions here, such that by doing so, they show that that event can be written as a matrix A times the vector y, or y is your data, your dependent variables, being smaller or equal than b. And here, of course, the matrix A and the vector b will depend on s, capital S, small s, and of course also on x. But if we can write it in this particular form, then suddenly it turns out that we can actually do calculations with that. In particular, such a shape is called a polyhedron. And this polyhedron is something that turns out that can be analyzed analytically. So we can actually find the distribution of our parameter estimator conditional on such a set. I'm not going through all the details, you can find those in the paper. It quickly still gets complicated, even though it actually is manageable. But this helps us to develop conditional inference. In particular, because we can also go back to what we wanted to condition on, which was not the signs, but just the variables being selected, by simply taking the union of this double event over all possible sign vectors. So we can go back from this to what the event that we were interested in, and in fact we can do that in two ways. One thing is we directly use what we have, so we condition on both, on the set of variables and on their signs. And if we can then do, for instance, a confidence interval with a guaranteed 1 minus alpha coverage probability, well, then we know that the event where we don't condition on this but only condition on the variables can again be written simply using this relation here as the sum over all these conditional probabilities where we also condition on the signs times the probability that we actually obtain such a sign. All, of course, conditional on the set of selected variables. Well, if you do that, then you can plug in what we have above here. We know that this is bigger or equal to 1 minus alpha. So plug 1 minus alpha in. It goes out of the sum, and you just end up with this summing over the probability of getting all possible signs, which of course is equal to 1. Therefore, this whole thing is 1 minus alpha, and so indeed, if you can control the probability over this more specific event, then you also control it over the general event. So that is one way to do inference, and that is the easiest way. Now, it turns out that we can actually also directly take the union over all these signs and directly look at exactly the conditional distribution that we're interested in. But of course, that also does mean that actually the theory becomes a lot more complicated. Now, the good thing is that there is a nice R package which implements this method. Now, there are some disadvantages to the selective inference method. I think the major advantage is that it's probably one of the most natural ways to account for an initial model selection step by simply conditioning on it. The disadvantages are that, yes, although we do get uniform inference, so that is clearly an advantage, the method does rely on the distribution of the error terms in the conditioning step. because we need to get these explicit results, we have to make some assumptions on distributions. Otherwise, this will not be infeasible. It will not be feasible anymore. It does turn out that we can generalize, and so there's an asymptotic version now as well available, where this to some extent can be generalized, but of course this remains a tricky thing with selective inference, and that for instance also means that it's difficult to see how you could extend it, for instance, to a time series setting. Another disadvantage that we have is that if you compare it to POSI, this conditioning, because we need to derive that explicitly, really relies on the problem that we are facing. So it's specific to the loss here in the solution. If you want to do a different model selection method, you can still use selective inference, but you would really have to treat that separately and do the whole analysis of how to end up there again, unlike POSI, which is an all-purpose method. Well, given the fact that they both use the sub-model view, I think these are the two natural alternatives to compare. On the other hand, then to go back to an advantage, given that we condition rather than saying we cover all possible models, you will get much narrower confidence intervals than you would get using POSI, which of course is a good thing. So there are some positives and negatives on selective inference, but it's mostly from a conceptual point of view a very nice addition to our toolbox to perform high-dimensional inference.